So we're the Back Row Achievers. The group consists of myself, Robert, Arvid, and Braden, and we chose to do the automated car model design. And our car is a 2016 Subaru Impreza WRX. So some background info about driving is that there's about 72,000 crashes annually in 2013, 44,000 injuries, and 800 deaths due to these automated crashes or automotive crashes. And a third of these deaths were due to drunk driving, and there was about 10,000 deaths due to drunk driving in 2015. And so this brings us to why we want to automate driving. So if we automate cars, that'll take a large part of the reason behind car crashes out of the equation. A lot of the human error that's a cause of car crashes will be eliminated, and there will no longer be the danger that drunk driving poses to the road and to people on the road. So our design goals with this project was to design a feedback loop that allows the car to accelerate up to 60 miles an hour, which simulates it getting up to speed on a highway. So 60 miles an hour or 27 meters per second. We wanted to keep our percent overshoot under 10%. We wanted a 0% steady state error so that we reach that 60 miles an hour directly. And we want a rise time below 8 seconds so that the car quickly gets up to speed.
So the car we chose to model was a 2016 Subaru Impreza WRX. It has a curb weight of about 1,500 kilograms. It has a 0-60 time of 5.2 seconds and a top speed of 65 meters per second or 140 miles per hour and a power of 268 horsepower. The physical parameters we got out of the data, we received a max force using the average acceleration of the car between the 0-60 time or 0-27 meters per second and the drag coefficient we received from its top speed. We modeled it linearly throughout its velocity. So using the physical parameters, we determined that the max force output from the car was 7,800 using Newton's second law of F equals ma, using the master car at 1,500 and the acceleration between 0 and 60. And we got a drag coefficient of 120 using its terminal velocity, where force due to drag is equivalent to the force outputted by the engine, giving us this plot of velocity over time.
Okay, so using the previously found plant function, we implement a p-type controller here. Here we can see the step response of the system that we acquired. We used SisoTool iterations to find a gain coefficient of 600. Here we can see our step response reaches a terminal velocity of approximately 22.5 meters per second, which is a 4.5 meter per second steady state error. This leads us to implement a PI type controller. So here we can see the step response of our PI type controller. We use SisoTool iterations again to find our two gain coefficients of Kp and Ki being 450 and 50 respectively. In our step response, we can see we had a percent overshoot of approximately 3%, which is well within our 10% bounds, and we achieved our steady state error of being 0. Here we also have a rise time of 6 seconds, which is less than our 8 seconds we wanted. This 6-second rise time is good because it's realistic to the ability of the motor, and it also is faster than the 8 seconds, such that an autonomous network of vehicles would flow more smoothly, as would traffic in general when you merge more quickly. To test the realism of this system, we then check the force demanded by the system as a function of time as the car accelerates. We find initially the car demands approximately 9,000 newtons versus the car's ability to supply 7,800 newtons. Since it only demands approximately 1,000 newtons more than possible to apply, and it only demands it for approximately a second, we decide that it is a negligible amount and decide not to implement a PID type controller.
Now we can check the controller stability using this Nyquist diagram. You can see that because there are no right-hand planes, or right-hand poles, because the transfer function is 1 over 1500s plus 120, and that the Nyquist plot does not have any clockwise encirclements of the -1, 0 point, that it is a stable system. We can begin to see from this Nyquist diagram that it will have an infinite gain margin. And that comes from the fact that the gain margin is like a multiplier for this Nyquist plot. So because this point here is at 0, 0, there is no multiplier that would bring it so it crosses the -1, 0 point. So there will never be a clockwise encirclement of that. We can also tell that the phase margin is around 90 degrees because it would take around that much rotation to, again, bring that point inside the Nyquist plot. To elaborate on the phase and gain margin, we use this Bode plot. So first off, to find the gain margin, we look where the phase is equal to -180 degrees, and it isn't at any point on this Bode plot, so that implies an infinite gain margin. And then to find the phase margin, we find the crossover frequency, which is where the magnitude is equal to 0 decibels, and we found that to be 0.309 radians per second. And then the difference between the phase at this crossover frequency and 180 degrees is the phase margin, and that was 84.7 degrees. To find the acceptable time delay, we use that same crossover frequency, which is omega here, and then our phase margin. And then to find the acceptable time delay, it is the phase margin divided by the crossover frequency. And we found that to be 4.784 seconds. So some of the limitations of this model is that in this model, the drag force is linear. So this line here is our model drag force. And then this quadratic is our realistic drag force. And because they're both found using a top speed of 65 meters per second, there's quite a big difference between them at the 27 meter per second target velocity of our model. So the difference between these two types of calculating drag is around 2,000 newtons. And so this means that our model would likely have a higher percent overshoot than we are anticipating because of that difference. Also, the model assumes a linear power output, and for most traditional cars with a normal either automatic or manual transmission, there isn't a constant power output. So this model is best used with either an electric car or a gasoline car with a CVT transmission.
Good afternoon, Professor Coulson. Thank you for the great semester. It's obviously your favorite back row achievers, not slackers. I hope you have a great summer.
Peace.